Thank you for the introduction. So the topic of my talk today will be the effect of hydrogen on plasticity in advanced high-strength steels used in automotive applications. And I also want to acknowledge my co-author who have contributed significantly to the results in the presentation I will give today. So a little bit of background. What we really want to investigate in this work was how the microstructure interacts with the hydrogen on a microstructural level. So why do we want to do this? Well, normally you want to know the relations between the processing structure and properties and performance to do a proper material design. In this talk, we have been focusing on the structure properties relation. And how do we do this? Well, we did choose one single alloy. And from this alloy, we did several heat treatments to get different amount of retained austenite, which I will show in the coming slides. And of course, we did some charging and checked about the hydrogen effect in these types of steels. So in order to get these different heat treatments, we used Glebo, which is a good thermomechanical device, which we have in our company as well. So you can perform a lot of different temperature cycling and deformation, etc. In this case, we used it for producing 5 different types of complex microstructures that we evaluated during this project. So in order to evaluate the properties, we did some mechanical testing in form of tensile testing. And here we can see the geometry of the tensile test that we performed. And here we can see the actual sample being heat treated in the Glebo setup. What is good with this type of material is when you do EDM cutting here, you will also have some extra pieces that is very suitable for material characterization. And it's also very good that you will have the immediate area that you're actually testing in the tensile test to have a good characterization of the structure. And in this project, we did both electron backscatter and XRD. We also did charging with the hydrogen and checked the results with TDMS. So what we did produce were 5 different types of complex steels. Well, the first one is quite simple. It's just quenched and tempered martensite. But then we have 5 different amounts of retained austenite. And these structures is quite complex. So it's basically a mixture of bainite, martensite, and ferrite. What you can see below here is the phase fractions from the EBSD maps. And the red part is the ferrite, while the blue is austenite. You also can see some areas that is unindexed, and this is probably fresh martensite which haven't been indexed by the EBSD. And that is one of the reasons why the measurement of retained austenite is usually not as accurate in EBSD as it is with XRD. So the values for the retained austenite has been provided from XRD measurements. So for the hydrogen charging, we used this recipe, and it's basically based on the paper from Van der Wendt. And yeah, you can see the poison here that we're using and the other parameters. What is important to highlight is that we also wanted to have deep trapping of hydrogen in our material. And to do this, we actually need to add a load to the sample during the charging. And I think this is a key component to have the correct charging we wanted to achieve. Yeah, so what you will see on the right when it comes back up is basically a diagram illustrating the TDMS results. So you have on the left side, you have the diffusible hydrogen, and to the right, you will have the deeply trapped hydrogen. And below you will have the reference sample, which wasn't charged at all. So we also did some tensile testing. And as you can see, the curves differs quite a lot depending on the retained austenite content. And you can also see that when you have a low amount of retained austenite, you have a very local fracture. And this means that you have basically a lot of area reduction where the fracture is. When increasing the amount of retained austenite, you will go towards a more global fracture. Basically, you have this more trip effect where you have a globally deformed sample, and it also results in a less area reduction at the actual fracture. So one thing that is quite nice when you plot it together is if you take the elongation at the maximum load and plot it towards the retained austenite, you have a really nice correlation between the retained austenite and the elongation. So in order to illustrate this type of fracture, it's quite usual to use this global and local formability analysis. What can be said up here is also the martensitic example. The one to the left is the uncharged, while the one to the right is charged. And you can see that the local formability has decreased. I will come back to that more in the later slides. But to explain this diagram, so you have a global formability index, which is the true strain at necking, that will be on the x-axis. And then you have a local formability index indicated by the true fracture strain, which actually also account for a fracture surface in the fracture. And then you have some indexing of, this is essentially this line, which indicate the formability of the material. And then you have these numbers, which is more arbitrary definition, but it helps to define which kind of properties you will have in the materials. So what happens when you charge, and how will that results look in the results? Well, we can see in all of the samples that we see a significant effect of the tensile testing between the reference sample, which would be the uncharged, and the charged sample in all 5 materials. So let's go a little bit more into the depth of the different things we can observe. So if you look at the true fracture, local deformability, we can see that it decreases for all 5 materials. If we continue to look at the true strain at necking, we can see this only changed for 4 of the 5 materials. What is interesting, or what should be noted here, is it did not change for the sample that did not have any retained austenite. So this change in true strain at necking is very well correlated to the retained austenite in the sample. And this can also be seen when you plot the uniform elongation after charging with respect to the retained austenite. That the severity of the changes has a very strong correlation with the retained austenite, as you can see here. Yeah. So some conclusions. Well, while charging, one thing that we could see is that we have an increase in the strength of the material, while we also have a decrease in the strain, or the possible elongation of the samples. So we have significant changes in the material behavior. And one of the most, characteristic drops is probably the drop in this local formability. You could also see that you have a drop in the global formability, and which also strongly correlated with the retained austenite, or the amount of retained austenite in the samples. So why is this essential for the automotive industry? Well, let's say that you have a crash box or something that you design with a certain property where you expect it to absorb a certain amount of deformation or have some characteristics in its function. But this type of properties changes than you expose it for hydrogen. That's why it's important to really understand the effects of hydrogen and its influence on mechanical properties, such as the plasticity and the relation to the retained austenite. Thank you for your attention, and I guess we have some time for questions.